Hey class! Today we will do a thorough runtime analysis of hash table operations. This video is part 3 of a multi-part series on hash tables. This video assumes that you are already familiar with the basic operations of a hash table, the separate chaining and open addressing methods of collision resolution, and big O notation. If you need a refresher on any of these topics, I will leave some links in the description below. First, a preview of what we will be learning today. We will be analyzing the operations insert, lookup, update, and delete. We will do this in the context of separate chaining and open addressing collision resolution strategies. Within open addressing, these analyses specifically apply to linear probing, quadratic probing, and double hashing methods of open addressing. For our runtime analysis, we will be assuming a good hash function, because if we don't, there is no upper bound on how inefficient your hash table can be. We will analyze the average case, the worst case, and do an amortized analysis for insertion. Before we dive into runtime analysis, let's do a brief recap of hash tables. A hash table is an array of buckets. It stores key-value pairs and uses the hash function on the key to calculate the hash value. It then uses the hash value to assign the item to a bucket. A hash table can have a collision when two keys hash to the same value. One collision resolution strategy is separate chaining. In separate chaining, each bucket contains an array or linked list. When there's a collision, we address this by appending the item to the end of the bucket. When the load factor exceeds a certain threshold, for example 1.5, we resize the hash table, typically doubling it in size. As a reminder, the load factor is equal to the number of items divided by the number of buckets. Another collision resolution strategy is called open addressing. In open addressing, we address the collision by inserting in a different empty bucket according to some pattern. The patterns we learned about are linear probing, quadratic probing, and double hashing. When the load factor exceeds a certain threshold, we resize the hash table in order to avoid clustering. A good hash function can reduce the amount of clustering in the hash table, which brings us to our next recap. Recall that a good hash function returns a valid index, is deterministic, is efficient, and is uniform. For the rest of this video, we will assume we have a good hash function. First, we will analyze insertion. We will do this by breaking down the insertion into steps and analyzing the runtime of each step. First is separate chaining. If the insertion would make the load factor exceed the threshold, we resize the hash table. This means we allocate the new hash table and rehash all existing items. Then, we hash the key and append the item to the end of the corresponding bucket. The process is similar for open addressing, except instead of appending to a new bucket, we follow the insertion pattern until there is an empty bucket. As for runtime analysis, some of these operations we can take care of right off the bat. Allocating the new hash table happens in constant time, and so does hashing the key. Again, assuming a good hash function. Now let's look at the other operations. First, we will look at appending the item to the end of the bucket for separate chaining. We will first cover the average case where there is no resizing. To analyze this, we ask ourselves, how many items do we have to traverse before inserting? Recall that the load factor is the number of items divided by the number of buckets. This means that the average chain size is equal to the load factor. So on average, it takes O of load factor to traverse the bucket and O of 1 to insert the item. Remember that the load factor must be less than a constant, otherwise we would resize the hash table. Then, O of the load factor is equal to O of 1, so the total cost of this operation is O of 1. Then, the average case insertion without resizing is O of 1. Now, let's look at the worst case insertion without resizing. The worst case would look something like this, where everything hashes to one bucket. Note that even if you have a good hash function, this can happen due to an adversarial input. This could happen when someone knows your hash function and deliberately crafts a sequence of inputs such that they all collide. In this case, it would take O of n to iterate over the bucket and O of 1 to insert, resulting in an overall cost of O of n. Then, the worst case insertion without resizing is O of n. Now, what about when we need to resize? Let's look at the cost of rehashing all existing items. In the average case, rehashing will look something like this. We have our old hash table and our new hash table, and when we rehash, the items are spread out pretty uniformly across our new hash table. It takes O of 1 to reinsert one item, and there are n items, for a total of O of n runtime. Then, the average case rehashing takes O of n time. But how about the worst case? In the worst case, even after resizing, everything still hashes to the same bucket. Then, the first reinsertion takes O of 1, the next O of 2, and so on and so forth, all the way to the last reinsertion taking O of n time. There's a formula for this summation which ends up being O of n times n plus 1 over 2, which is O of n squared. Then, the worst case rehashing takes O of n squared time. Now that we have analyzed each individual step for separate chaining, we can take a step back and look at insertion with separate chaining as a whole. In the average case, the most expensive operation is O of n, so the average case insertion is O of n. In the worst case, the most expensive operation is O of n squared, so the worst case insertion is O of n squared. Now let's look at open addressing. First, we will look at the step where we follow the insertion pattern until we encounter an empty bucket. We will first cover the average case where there is no resizing. To analyze this, we ask ourselves, how many items do we have to traverse before inserting? The number of items we have to traverse before inserting is related to our cluster size, so traversing the hash table is O of the cluster size. Then inserting the item is O of 1. Since this is the average case, and we are assuming a good hash function, we can assume the average cluster size is a constant. Then this becomes O of 1, and the total runtime is O of 1. So, the average case runtime for insertion without resizing is O of 1. Now let's look at the worst case insertion without resizing. The worst case will look something like this, where all the inputs form a really large cluster. Just like with separate chaining, even if you have a good hash function, this can happen due to an adversarial input. Here, it takes O of n to traverse the cluster, plus O of 1 to insert, for a total of O of n runtime. Then, the worst case runtime for insertion without resizing is O of n. Now let's look at what happens when we rehash. In the average case, there's not much clustering when we rehash. Each reinsertion takes O of 1, and there are n reinsertions, for a total runtime of O of n. Then, the average case runtime for rehashing is O of n. In the worst case, even when we rehash, all the items form a large cluster. Then it takes O of 1 to reinsert the first item, then O of 2, and so on and so forth until the nth item. This is the same formula as last time, which we know to be O of n squared. So, worst case rehashing takes O of n squared time. Now that we have analyzed each individual step for open addressing, we can take a step back and look at insertion with open addressing as a whole. In the average case, the most expensive operation is O of n, so the average case insertion is O of n. In the worst case, the most expensive operation is O of n squared, so the worst case insertion is O of n squared. To summarize, runtime analysis is the same for separate chaining and open addressing. The average case runtime for insertion is O of n, and the worst case runtime for insertion is O of n squared. Oh hey, it's Tim the Turing Machine. Hey Tim, what's up? How did this happen? What do you mean, how did this happen? We just did a very thorough runtime analysis. You saw exactly how it happened. That's as bad as an array? Yeah, you have a point. This does seem pretty bad. But it's not as bad as an array, and I have just the trick for showing you why. Amortized runtime. It helps us answer the question, what is the runtime averaged over a sequence of operations? Let's delve into amortized runtime analysis. Amortized runtime helps us analyze operations when operations are cheap most of the time, but occasionally expensive. For example, insertion in a hash table is usually O of 1, but it is O of n when we need to resize the hash table. While it is correct to say that insertion is O of n, this loses the valuable information that most of the time, insertion is only O of 1. So, amortized runtime tells us the runtime when averaged over a sequence of operations. Let's look at an example. Say we want to insert Sarah Puppy into this hash table like so. The cost of doing so is O of 1. Now maybe we want to insert Serena Lollipop. The cost of doing this is also O of 1. Then we keep inserting until at some point, one more insertion would cause us to exceed our load factor threshold, in which case we need to resize the table. Then we allocate the new table and rehash all existing elements in a process we know takes O of n time. Then we insert the new item, which is O of 1. Let's calculate the total cost of all our insertions. We had n constant time insertions, followed by rehashing, which is O of n, and then we had one more insertion. This is O of 2n plus 1 total. But what we're interested in is the cost per operation. So, we divide by the number of operations, in this case it's n plus 1, and we get the cost per operation is constant. This means that insertion still is O of n, but it is amortized O of 1. Now we can update our summary to include this information. But wait, what's the difference between average case and amortized? Great question, Tim. It's easy to confuse the two. Let's go over some of the differences. Average runtime is the runtime of the average operation. It is useful when there is variance in the runtime. For example, in our case, some collisions are longer than others. It is also useful when there is a degree of randomness involved, like in random trees. Amortized runtime is the runtime averaged over a sequence of operations. It is useful when most operations are cheap and few operations are expensive. For example, most insertions are cheap, but sometimes we need to resize the hash table, which is expensive. In our case, it's true that there is variance in the runtime, and we mostly have cheap operations with few expensive operations. So for a hash table, it's useful to look at both average runtime and amortized runtime. So to summarize our extremely thorough runtime analysis of the hash table insertion, the average case runtime is O of n, the worst case runtime is O of n squared, and the amortized runtime is O of 1. But people usually just say hash table insertion is O of 1. While our runtime analysis was extremely thorough and technically accurate to the definition of big O, it is also important to note that colloquially, people are usually talking about the amortized runtime when they are talking about hash table insertion. So, if you're talking to a friend or a coworker or a job interviewer and they tell you how much they love O of 1 insertion of hash tables, maybe don't go on a huge rant correcting them. Even though insertion is technically not O of 1, when people talk about hash tables, they are almost always referring to the amortized runtime. So the next time someone tells you how much they love O of 1 hash table insertion, you can just smile and say, me too. So, all of that analysis was for insertion, and we still have 3 operations to go. Luckily, insertion was the hardest, so the rest should be a piece of cake. The steps for lookup are pretty simple. We hash the key, and depending on whether we are using separate chaining or open addressing, we either iterate through the bucket or follow the insertion pattern through the hash table. We already know that hashing the key is O of 1. Now let's look at iterating through a bucket. This is a lot like the step in insertion where we iterated through the bucket to append an item. The only difference is that for lookup, we don't have to insert anything into the bucket. But the iteration is the same, so the runtime is the same, which is O of 1 in the average case and O of n in the worst case. Now let's look at following a pattern in the case of open addressing. This is also similar to insertion, with the only difference being that we don't actually have to insert. Then the runtime is the same, so we have O of 1 in the average case and O of n in the worst case. Taking a step back and looking at lookup as a whole, we see that lookup is average case O of 1 and worst case O of n. Now that we have analyzed lookup, the rest of the operations are really easy. For update, we look up the key and then we update the value. We know that lookup is average case O of 1 and worst case O of n, and updating the value is O of 1. Then, update is average case O of 1 and worst case O of n. Delete is very similar. We look up the key and then delete the key value pair. Lookup is average case O of 1 and worst case O of n, and deletion is O of 1. Then, delete is also average case O of 1 and worst case O of n. Let's summarize what we've learned today. We learned that average runtime is the runtime of the average operation, and amortized runtime is the runtime averaged over a sequence of operations. Colloquially, when people talk about hash table runtime, they are usually referring to amortized runtime in the case of insertion, or average runtime in the case of the other operations. We also learned that although we arrive at the runtimes through different means, the runtime analysis ends up being the same for separate chaining and open addressing. We did a thorough runtime analysis of hash table operations insert, lookup, update, and delete, analyzing the worst case and average case, and amortized case for insertion. These can be summarized in the table here. Thank you so much for watching, and please, feel free to comment any questions you have about the video or any topics you would like me to cover next. I also welcome feedback for how I can improve my videos. As always, this is your CS Professor of Fun.